Good everyone. Um, I got top scholar in physics in 2024, and this is my paper. I'm going to walk through it as an exemplar for any future students wanting to take physics scholarship, even level 3 physics. I'm just going to go through it and explain what my thought process was and just sort of show you how they expect you to answer questions at a high level as an exemplar. I got 8.8. This is my own writing, by the way. I got 8.878 for 31. So no one got 32. Obviously, that is the maximum score. I dropped a mark in question 3, and I'm pretty sure I know where too. Other than that, I pretty much got it all right. So we're just gonna go through it, and I might make some annotations, and a few little ticks here and there, and we'll see what happens. My pen is actually the wrong size for some reason. Oh well. So here we go. So the first question was on capacitors. And unlike past years, I mean, the whole question was capacitors, really. If you didn't really know how a capacitor worked, you're a bit screwed. But that sort of speaks to scholarship physics. They do focus in on a few topics sometimes, so you've got to have this wide knowledge, otherwise you're going to get screwed if you don't know this thing which the entire question might be focused on. Anyway, so they gave you a very simple circuit, right? There's not even a resistor in the circuit, but you can presume that wire has resistivity, I suppose. Battery, switch, and a capacitor. And they gave you some measurements in centimeters and 50 volts. So you got to show that the charge on the plates is 2.5 times 10 to the minus 8 coulombs. This is like a show achieved sort of question at level 3, to be honest. You get your equation, C equals E naught times ER times area times divided by distance. So we got the permittivity of free space times 1, because that's the relative permittivity of air, times the enclosed area, which is just 52 centimeters times 88 centimeters. So remember SI units, put it in meters, and then divide by 0.8 times 10 to the minus 2 meters, or 0.8 centimeters. And you get this many farads, and then we apply Q equals CV. So Q equals this times 50 volts, and you get this number, and then you round to 2.58. And that's 2SF, and it says explain why the value should be 2 significant figures. And the question of measurements provided the lowest number of significant figures is 2, hence why the answer is rounded as such. So, 2 significant figures are shown everywhere. Except 50, oh no, 0.0. Yeah, that's a bit weird, but whatever. So that's a tick. I'd say that's worth 1 mark. That's very, very basic. Explain why the amount of energy stored in the charge capacitor is only half the total amount. There's a reason they've not said justify, they've just said explain, because the actual reason is very complex, but you just have to say, as it charges, half the energy carried in the electrical current does not make it onto the plates. The capacitor, which the capacitor does store energy in electric field via charge separation, and is returned to the battery or lost as heat to resistance. I don't know if this is correct here. It might be wrong. I think that is the correct thing. But that's probably worth a mark again. Yeah, so you never actually had to say why, you just had to explain, sort of, that it does. Anyway, here we go. Tank can be filled with non-conducting oil with relative permittivity of 1. Right, so this is where the exam wraps up a bit, gets a little bit harder. So read through the question. There is a valve in the bottom of the tank that can be opened to drain the oil from the tank. So the switch is open. So when she closes the switch, the capacitor charges up, and it holds the 50 volts across it, 50 joules per coulomb. That's basically what this question was, right? The switch, she closes the switch and connects the battery. What do you do? So she closes the switch, it charges, there's now 50 volts across the capacitor, because it has to directly oppose the battery, if you remember Kirchhoff's law. Step 2, fill the tank with oil. Right, so filling the tank with oil is putting a dielectric between the plates. And so more charge can now fit onto the plates. This is a little bit hard to explain or understand, but essentially the electric field gets a bit weakened. So, or the net electric field gets weakened because the oil creates an electric field that opposes it. Anyway, more charge gets onto the plates, and so more flows from the battery. Since the voltage across the capacitor drops below 50 volts, it has to reclimb again. Now it drops below 50 volts because the if you remember, voltage equals Q divided by C. If the capacitance increases, then voltage will decrease. And it has to reclimb again, so it's charging up to 50 volts again, and that's putting more charge on it. Now, when you open the switch, the circuit gets broken. Like you can see, it's not connected here. Now, there's still 50 volts across the capacitor, and it will hold its charge. The reason for this is quite technical, but the break in the switch, the break in the circuit, is effectively an infinite resistance, and so the time constant will go to infinity, and therefore charge doesn't flow off the plates. And in step 4, when you drain the oil from the tank, the capacitance is reduced back to the original, but there's still more charge on the plates. You know, there's more than 2.5 times 10 to the minus 8 kilograms of charge. The charge can't go anywhere, but the capacitance is lowered, so V must have increased. If C goes down, V must increase to keep Q constant beyond 50 volts. And I'd say that's probably 3 marks there. Or maybe 2 marks. I'm not sure. This is just a calculation question. The capacitance with the oil will be the original capacitance multiplied by 2.1, because that's the dielectric, and therefore Q will be the new capacitance times 50 volts, which equals that. And when the oil drains, C returns to this, so the new voltage is 105 volts. I'm pretty sure you could have actually just taken 50 volts and multiplied by 2.1 to get 105 volts as well, but this way works too. So that'll be 1 mark. Right. So this time she fills the tank with oil and closes the switch. The potential difference across the place 50 volts. So when she does that, the charge will be 5.32 times 10 to the minus 8 coulombs. And she opens the valve and the oil drains from the tank at a constant rate. So you know that after 12 seconds, the charge on the plates will be 2.53 times 10 to the minus coulombs, because that's what we 10 to the minus 8 coulombs, because that's what we calculated. And you can calculate that the starting value is this, so it must just be a linear descent. And then after that, no movement of charge occurs, so it's just going to be flat. So flat line. And this will be its constant. So there you go, that's the graph. I think I labelled it well enough. Now the last question was the hardest in this section. There's this new plate that's been put between the 2 original plates. It's the same height as the 2 original plates, but only half the width, and has negligible thickness. That's important. Using appropriate physics concepts, explain the effect that adding the 3rd plate will have on the total capacitance of the tank. So, here is where I would recommend your first 2 lines to these big questions need to completely display to the marker that you understand what is happening. Okay? So, capacitance depends on exposed surface area between the plates that can be used to store charge and on an electric field. That communicates you know what capacitance does. By adding the thin plate, the system is now 1 plate of half exposed area and 2 plates of half exposed area and half distance in series, with everything in parallel with each other shown below. That seems a bit confusing. It's like this. This is the battery. This is the wide plate here, this bit, and these are the 2 thin bits here and here. And you can calculate the capacitance of this area. You can calculate that capacitance, and you can calculate the capacitance of these 2 areas as well, shown here, and then you simply have to add them for this bit, half it for this bit, and then apply the 1 on C total. Oh no, hang on. For these two, you add with like 1 on C total equals 1 on C1 plus 1 on C2. And for this bit, you just have it, it's this, and then you add them up. If you don't know how to work with parallel capacitors or series capacitors, then I suggest you go back to working at level 3 for a bit until you get that. But the main conceptual breakthrough is to understand that this diagram is the same as this diagram. Once you're there, it's easy to say that the net capacitance is half in one branch, but capacitors in parallel add, so the half capacitance added to another half capacitance, and so actually the net capacitance is unchanged. And all of that gets you 8 for the section. I'll just leave that there if you want to pause the video and read the response a bit further. Right, martial arts. So these are the rotational inertia questions. So let's hop straight into it. You don't really need to read the background, it's all useless. Show that the time taken, t for the staff to the bottom slope is given by this expression. It's not too bad. You conserve energy, so potential energy at the top will equal kinetic energy and rotational kinetic energy at the bottom. So your mgh equals half mv squared plus half iw squared. This is I, that's I, and that's w squared. You divide through, yes, since I equals this, divide through by m, you get gh equals 3/4 vx squared, vf equals vx. Final velocity at the bottom. 4/3 gh equals vx squared, so vx equals 2 times the square root of gh on 3. So that's all very good. You have vf, d equals vi plus vf divided by 2 times time, like average velocity times time. So rearrange for time, sub vf in, vi is 0, rearrange, and it stills out. If you want to just, I'll leave that there if you want to just pause. That'd be worth 2 marks probably. Yeah, so for these sorts of questions, you really have to just think about energies first. So always go, what energy do I start with, what energy do I end with, and you'll find the result can fall out quite easily. Okay, right, referring to relevant physics principles, discuss the validity of these two statements. An object with fixed mass to have linear acceleration, it must experience a non-zero net force. This is a very basic statement, and it is just a discussion of Newton's law, F equals ma. Acceleration in a linear direction is equal to the net force in that direction divided by the mass of the object. So a high force, high acceleration, high mass, low acceleration. If the net force is 0, an object can still be moving, but it cannot be accelerating. So for example, terminal velocity, when you have an object falling, the force upwards from air resistance is equal to the force downwards from gravity, and it will not accelerate, but it'll continue falling. Now, that's probably a good enough answer there, but you know, we could go a little bit further and say, from energy standpoints, for an object to accelerate, it must gain kinetic energy, but must have come from work provided by a linear force. Therefore, in order to accelerate, a non-zero net force in a given direction must be present. And so that's all very well and good. Statement 2 is tricky. It seems like a similar argument should come into play. Angular acceleration, it must experience a non-zero net torque. The key difference here is rotational inertia can be changed, mass inertia cannot. So angular acceleration can be supplied by work. Imagine a man spinning on a chair, holding weights with his hands outstretched. Now, when this guy draws his hands inward, the rotational inertia of the system lowers. I'm sure you've seen these sorts of examples doing level 3 rotational inertia questions. The angular velocity must increase because without an external torque, angular momentum is constant. So to increase angular velocity, the system must have experienced an angular acceleration. So the rotational energy supplied to increase W came from work done by the man's arms, not an external net torque. And then as a side note, work and torque act orthogonally to each other. So work and torque act at right angles for an object. So torque causes an object to rotate, work causes an object to move along a line. This is very important to understand, that rotational inertia of a system, don't know why I've drawn that, can be changed using internal torques, not external. Okay, on to what I would think is the hardest question in the paper, is the rotational inertia question. This took me a while to get. Essentially, they tell you the rotational inertia of a stick of length x from a center of rotation on the edge is 1/3 mx squared. Then they give you this new stick with a center of rotation in the middle, d away, and you've got to show that the rotational inertia is this expression. And this looks very weird, right? You know, where's the 12th come from? D squared, L squared. Where did it come from? The key is to imagine breaking the stick at that center of rotation into two pieces, and then consider them as two sticks, as in diagram 1, rotating off the end. So the mass to the right of the stick is L on 2 plus D divided by L times M. The reason for that is L on 2 plus D is this distance here, like this distance here, that's L on 2 plus D. And if you divide that by the total length and multiply by mass, you get the proportion of the total mass that this piece of the stick represents. So the rotational inertia to the right is 1/3 times, why have I got 2 m, oh yes, L on 2 plus D divided by L times M is 1/2 plus D on L. So 1/3 times that, 1/2 m x squared. L on 2 plus D is the x squared bit. And you can simplify that to that, and you can simplify that to that. The left-hand side has a similar trick. L on 2 minus D divided by L is the proportion, this length here. You multiply that by M to get the mass of the left-hand side. So 1/3 times 1/2 minus D on L times M times the x squared bit. Simplify that out. And if you add them up, a few things cancel, and you get this, and then you get this. So that was really tricky conceptually. You just have to have faith that you're doing it right, and the answer falls out at the end. Alright. The next question is part D. I actually wrote a very similar answer, but on the back page. Well, we'll read the question first, actually. So we got the stick rotating as described above, sort of thing. We got F1 and F2. Right, so discuss the relative sizes of F1 and F2. That's F1, that's F2. The center of rotation does not move. That's very important. So I said the right-hand side of a higher inertia, so F2 must be bigger than F1 if both of us apply the same angular acceleration around the center of rotation. I don't know if that's really a perfect answer, but I did still get 8 for the section, so it probably is a little bit right. And then this question, the sideways strike, can be blocked. Essentially it's saying if someone swings a stick at you, how should you best hold your stick? And this is very aptly described by the diagram, as you can see. The blocking force should apply a torque against the one being generated. The force should be at right angles to the motion of the end of the staff and as far from the axis of rotation to maximize torque. Like, this is good. He's done a good job, the blocking guy, because he's really going to hit this guy hard. Massive torque against his center of rotation and cause him to stop swinging. These arrows are swinging staff to a top, and you defend it. You're not going to wait to buy a stick. So that's all very good. So I got 8 for that section as well. This is the question I got wrong, I think. So there's this wire with resistivity R. The piece of wire is bent into a circle, and there's this theta angle between these 2 points connected by a resistance meter. The conceptual way of doing this to find the total resistance of the loop between the 2 points is to realize that it's a parallel circuit. I did not realize this. I found the proportions, so theta on 2 pi for this bit, and 2 pi minus theta for that bit, and then I sort of just bullshitted. Like, I multiplied the proportions and times it by r, and the answer falls out. That's not the correct way of doing it, okay? The correct way of doing it is to apply 1 on RT equals 1 on R1, which is theta divided by 2 pi r, plus 1 on R2, which is 2 pi minus theta, 2 pi minus r. And when you solve for RT and multiply things around, this answer falls out. Explain using physics concepts where point Q should be placed to the largest value. So Q should be here. So it should be directly down. You've made both paths the same length. And when both paths are the same length, the resistance will be a maximum in a parallel circuit. So arc length traveled is maximized and hence effective resistance is maximized. Yeah, and then they ask you to sub in 10 into the equation. So that was a bit pointless, really. Anyway, that's all good. We got the square coil question now. A square coil of wire with mass m, resistance r, number of turns n, falls into a magnetic field. The effects of air resistance will be ignored, which is good. So you got to show that the terminal velocity is this. Now this looks terrible. It genuinely looks terrible. But you just have to stick with it. You write out your first line. Terminal velocity is achieved when the downwards gravitational force is equal to the upward magnetic force. So already you're thinking in terms of, well, mg is going to be equal to something. The magnetic force on each term is BIL, F equals Bill. So the sum of all the forces will be N times BIL, because it's N turns. The voltage on each is BVL, so the net voltage will be NBVL, because it's N turns. So, yeah, V equals IR, I will equal V divided by R, so NBVL divided by R. This little v is velocity. So, F magnetic equals N Bill, so N times B times I times L divided by R gives this expression, because I is NBVL divided by R. And if you equate Fg equals Fm, you get Mg equals this expression, and this does rearrange to Mgr on B squared L squared N squared equals velocity. You should draw a little arrow above your V to indicate a vector. Bingo. There are a lot of questions I've seen over the years like this, terminal velocity, equating magnetic and gravitational forces. So make sure you understand that. This next question is a bit strange. They let you pick M, N, and L. It's a bit strange why they do that, but whatever. So I've gone for 60 windings, 20 grams, and a 1 meter side length. So fairly big loop, fairly big coil, but it's light. You sub the numbers in and you get 54.5 meters per second. What do you do? When the coil enters the field, a voltage is induced by work done on charges across the side, right angles to the motion. So, yeah, this falls in. A current starts to flow from an induced voltage. Current flows anti-clockwise. The flowing current creates a magnetic field which acts to oppose the changing flux through the loop. So when this loop's falling through this field here, it's getting changing magnetic flux. So a magnetic field will be created out of the page to cause an anti-clockwise current this way around. The loop reaches terminal velocity when the induced voltage is large enough to generate a current which creates a force which opposes gravity. The coil gradually accelerates. Negative jerk. You don't need this. You can get rid of that. That's a bit advanced. If the whole loop makes it into the field, the flux no longer changes, so the force disappears. Opposing induced voltages occur and no current flows. This causes the core to accelerate from gravity beyond terminal velocity. Now this last bit is a bit pointless talking about because it says as it enters the field, not as it remains in the field. So talking about the loop being fully in the field was a waste of time. But that's all very well and good. That's still a fine enough description. A square coil is unwound. The same piece of wire is used to make a second square coil with side twice as long as the original coil. You got to think a bit here. Yeah, the effective length of the unwound piece is 4 times L times N because it's a square with L side lengths. So you got 4L, but then N windings, so 4LN. Now, if you want to make a square of sides 2L, the effective length would be 8L times the new number of windings. So 8LX equals 4LN, so X equals half N. So the number of windings is therefore halved, which should make sense. If you want to double the sides, so you got half the windings. The induced voltage expression is not changed. That's very important, since L being doubled is offset by N being halved. Because remember, voltage equals N VL. So N's halved, but L's doubled, so it won't be changed. The magnetic force expression is unchanged, since the length is doubled, but N is halved. This leads to an equivalent terminal velocity when dropped, since the resistance of the coil is still 1 ohm. And this does make sense. The same length of total wire is fallen, so the terminal velocity should be unaltered. So that's all very well and good. Now I only got 7 for this section. I think this part was pretty good. I just think I did not get full marks here, unfortunately. If I'd done it this way, who knows, maybe we would have been looking at a perfect score. And question 4 is on laser cooling. So this is waves and nuclear physics coming into the play. It's really freaky, but photons have momentum. Good luck understanding that. So here we go. A laser shone into a container. Energy of each photon is slightly less than the difference in energy between 2 electron energy levels in a sodium atom. So which sodium atom can absorb the photon from the laser? Well, they don't carry quite enough energy. Must be equal to the energy change of electron jumping between energy levels. The energy of emitted photons is slightly less than the required difference in energy, so the energy of the photons needs to be increased. Now, by moving towards the laser, the sodium atom can encounter more photons per second and hence increase their frequency, so that the energy is slightly increased to the required level. The sodium atom moving towards the laser can absorb a photon via a Doppler shift, essentially. The wavelength will be decreased because it encounters more wavefronts per second. I'm not sure whether it's strictly true to say it encounters more photons per second, hence increasing their frequency. That might be a bit of a poor explanation. But it's Doppler shifted, slightly higher frequency, and it matches the quantized energy change. So therefore it can absorb if the photon is moving towards. If the atom is moving towards. So, how can the momentum be effective? Well, the one moving towards it can absorb the photon, so the momentum of the photon is imparted onto the sodium atom. So to conserve momentum, the atom slows down so that the final momentum to the right equals initial momentum to the right. So if you think about it, if this momentum of the photon to the left just goes, it's gone, then the atom must slow down to conserve momentum. The one moving away can't interact. There's not a difference in electron energy levels that aligns with the Doppler shifted photon, so no photon absorption can take place, since electrons only occupy discrete stable electron orbits and cannot exist between them. So the left moving one is unaffected. Alright, a bit of maths here. I don't really want to go through the maths here. In fact, this might actually be wrong, so I'm not going to go through it. I'm going to leave it here if you don't want to read through it. It's just a conservation of momentum question, but in relativistic sort of scenarios. Maybe I got it right, maybe I got it wrong. You can still get an 8 getting a little bit wrong. So I'll leave it there. You guys can look at that if you want to. I'm not going to go through that particularly. But yeah. The last question is a bit of a break of the conservation of momentum. It's a bit scary. An atom can move faster than its original speed if the photon is emitted in the same direction the photon was originally travelling. So when the atom absorbs the photon, it slows down, but the apparent frequency of the photon from the sodium perspective is greater than the actual frequency of the photon, and the apparent wavelength is therefore shorter. The momentum of the original photon uses the true wavelength, not the Doppler-shifted wavelength. And so when the photon's re-emitted by the sodium, the energy change produces a photon of higher frequency than the original photon. So the new photon has a lower wavelength and hence a higher momentum than the original. It's lower wavelength, higher momentum. So although the sodium atom, the TLDR is, although the sodium atom is slowed down by the initial momentum change, the final momentum change is higher, so the sodium atom moves faster along its original trajectory. And I scored an 8 for that. So we had 8, 8, 7, 8 for 31. 32. Not quite an outstanding. A few people have asked me if I got Premier. I did not get Premier. I got 3 outstanding scholarships and 4 regular ones, which is like, and I was like 1 off on a few marks for outstanding and scholarship. I was very close, very close. I'd say I'm probably 13th or 14th, but I still got outstanding scholar and I got top scholar in physics, so I'm still very happy. It's very good. But that's that. Watch through the video and pause if you want to read the answers. I'm sure the marking schedule will get released at some point. You'll be able to see exactly what you were supposed to do in a few scenarios. But that's that one. So cool. Catch you guys next time.